Here we have an example of balanced design of simple components which are a part of an assembly of a hydraulic crosshead machine. This requires a little bit of explanation. What we have here is an enlargement of one half of a crosshead which is attached to a hydraulic ram. This type of component can be found in the mechanical engineering laboratories for compression testing of samples, or civil engineering laboratories would have a similar machine. The arrangement allows for all the heavy hydraulics to be hidden away in a cabinet so that you're free to insert the specimens as if it was just a bench. What the hydraulic ram does is exerts a force of 500 kilonewtons on this crosshead, and that force is converted into a tension in the two tie rods here of 250 kilonewtons each. So looking at this assembly of components, that force, down force of 500 kilonewtons is 250 each side. That presses down on this split washer, which is inserted into an annular groove in the tie rod. The reason for this is it allows easy disassembly of the whole, all the components. So the force, the down force, goes through the washer and presses down on this part of the tie rod, producing tension in the upper part of the tie rod. Now, before we disassemble the components in order to design them individually, we need to be able to visualize the forces acting on each of the components. So to do this, we need to follow the lines of force as they travel through the assembly. So starting with the 500 kilonewton force, this will travel through, split either side into 250 kilonewtons. It will then be transferred into the split ring by the platen pressing down on this top surface, which is an annular ring going around the outside of the split washer. The force travels through the split washer and exits the split washer on this bottom surface here by pressing down on the bottom half of the tie rod. So we have compression or bearing on the top and compression and bearing of the ring on the tie rod on the inside here. That force, which is of course distributed all the way around the annular groove, basically joins up and becomes a tension force of 250 kilonewtons in the tie rod. We're now going to determine the dimensions D2, D3, D4 and T by separating out the components and determining their modes of failure. Now we need at least as many modes of failure as there are unknown dimensions, in this case 4. We now need to determine the modes of failure for each component. The possible modes of failure for static design are tension, bearing or compression, shear, bending or torsion. This particular example does not have bending or torsion involved, but we have the other three failure modes: bearing, tension and shear. Let's start by designing the column. We need to visualize the modes of failure. We have the 250 kilonewtons acting under compression around the annular ring, being converted into a tension in the rest of the column. Now, in order to visualize the modes of failure, it's sometimes useful to make the component we're designing of a very, very soft plastic material and imagine its deformation under the action of the forces. Now, in reality, of course, the deformation is microscopic, a movement of a few microns at the most, and we're designing not for failure to occur but for a level of stress to be reached, which we call the allowable stress. But in order to visualize the mode of failure, as I say, it's sometimes useful to imagine that the components exerting the force are very hard, but the one we're designing is very, very soft and elastic, or plastic. So under tension, you could imagine that the smallest section will be the section to deform the most and be subject to the highest stresses. So that is where we would design the column under tension. So we design the column for failure in tension across the diameter D2 using our design equation. For tension, Sy on N greater than or equal to force over area. We use the value of Sy for the material that's going to actually fail, in this case the column, which is at 590 megapascals. Given the design factor of 4, the force is 250 kilonewtons, and the cross-sectional area taking part of the failure is pi d2 squared on 4. Gives a result for D2 of 46.5 millimeters. It's very convenient that the first equation or first failure mode only results in one unknown. Other failure modes may have more than one dimension that is unknown in the equation, so we have to leave it until we've got enough equations to solve for those dimensions. Now the next failure mode involving the column will be a bearing or compression failure between the split ring and the column, where it presses down on the column. The equation that we use is the same as for tension because it's compression. Now the value of Sy, because there are two components involved, both subject to the same failure mode and the same force, we must use the weaker of the two materials and design for that particular dimension. So the weaker of the two materials of the column and the split ring is the column. So we use the lower value of Sy in the equation. So again we have 590, design factor of 4, a force of 250 kilonewtons, and the area involved is the annular ring, which is pi on 4 d3, the outer diameter d3 squared, minus the already calculated value d2 squared, which we substitute from the previous equation, giving a result for D3 of 68.2 millimeters. Now following the line of force back up through the ring, we've already designed for bearing failure on the bottom of the ring. We now design for bearing failure on the top of the ring. Just as we did in the second bearing failure, same equation, Sy over N greater than or equal to F over A. Same principle involved. We have two materials in contact with each other. We have the body and we have the ring. We must use the weaker of the two materials in the failure mode. In this case, the value of Sy that we use is for the body, and it's 240 megapascals. Again, everything else is the same apart from the dimensions. In this case, it's the outer diameter D4 squared minus the diameter D3 previously calculated, which is 68.2 squared, giving a result for D4 of 99.8 millimeters. Now the final mode of failure that we're going to consider is the failure of the split ring in shear. If we draw the split ring separately, the line of force passes from the body, or from the crosshead, through the split ring into the column. Now again, in order to visualize the shear failure of the split ring, imagine the split ring is made of a very, very soft material and the rest is made of hard material. So as the crosshead presses down on the split ring, which in turn presses on the groove in the column, if it's a very soft material, you could imagine that it would shear where the dotted blue ring is shown. This will be across the diameter D3, and the shear area will be this ring of material, diameter D3, thickness T. Now because it's shear, we use the equation 0.6 Sy on N because ductile materials have approximately 60% of their strength in shear compared with tension or compression. The force is the same force as before. The material that's going to fail is the material of the split washer, which has a value of Sy of 810 megapascals. The dimensions involved are D3 and T, so the area of shear, note by the way that shear area is always parallel to the force, whereas tension and compression is always normal to the force. So the shear area, which is parallel to the force, will be this annular ring, diameter D3, so pi D3 T. We substitute the value of D3 from the previous equation and we end up with a value of T of 9.6 millimeters. We can now round up our dimensions to first or second preferred sizes. So D2 becomes 50 millimeters, D3 becomes 80 millimeters, D4 becomes 100 millimeters, and the thickness T becomes 10 millimeters. Now to finish the design properly, these are the actual sizes that we're going to be using in the assembly. We should substitute these back into these equations to calculate the actual design factor for each component. We then know that the one with the lowest design factor will be the first component to fail. Now if we want a particular component to fail because it's easy to replace or for whatever other reason, we simply make that dimension slightly smaller and we can then be sure that that component will be the first to fail.